Welcome everyone. Good morning. This is our fifth and last doctoral meeting session within the program of Aerospace Science, PhD program on Aerospace Science and Technology. Today we're going to be listening to six presentations, six ongoing PhDs on topics. It's a bit of miscellaneous, but topics related to mainly air navigation and control. We have three talks on optimal control, optimization algorithms for aircraft trajectories. Then we'll see a talk on airborne wind energy related to aeroelasticity by Ivan and so on and so forth. And then space systems, GNC and space systems by Alberto and Alison. So welcome everyone. Thank you very much to the speakers, presenters. Thank you also to the supervisors and the rest of the audience. Hopefully some more people will be joining.
Okay, I will start. Hello, my name is Abulfaz. I'm a first-year PhD student. I start working from September. My supervisor is Professor Manuel Soler, and the topic of my thesis is robust aircraft trajectory optimization for the benefit of climate. This thesis is funded by a European project, Fly ATM4E, and we participate in it. I will start my presentation by presenting briefly a state-of-the-art through the motivation, problem statement, and identification of a gap. Then I will continue it with addressing the gap by two high-performance trajectory optimization techniques, and in the end, I will briefly summarize the achievements and future steps. So, as we all know, aviation contributes to climate change through the emission of non-CO2 effects and CO2 emission. The non-CO2 effects are due to the NOx emission, water vapor, increased cloudiness due to the contrail formation, soot and sulfate aerosols. From the latest study on global warming, it has been reported that the aviation contributes to 5% of climate impact. However, the air transport industry is predicted to grow at 4.4% yearly in the next 20 years, which means the contribution of aviation to global warming is expected to increase critically. So the development of eco-efficient aviation is crucial. Here is the figure that quantifies the effective radiative forcing of each agent. The red one shows the warming potential, and the blue one is referred to the cooling. By looking at the last row, we can conclude that the non-CO2 effects are responsible for 66% of net aviation radiative forcing, and the rest is referred to the CO2. So regarding the mitigation strategies for CO2, the development of more efficient aircraft or use of alternative fuel or propulsion is required. However, the non-CO2 effects, which we're most interested into, can be mitigated using proper aircraft trajectory. The non-CO2 effects actually, which trigger approximately 2/3 of aviation RF, highly depend on geographical location, altitude, time of the emission. So, by planning the trajectory such that those climate-sensitive regions, those regions that strongly enhance the non-CO2 effects being avoided, would be beneficial and can reduce the climate impact of aviation. For example, we can see the countries actually for where the ambient temperature is low at higher altitude. So we can avoid it by proper flight planning. So the objective is determination of aircraft trajectory such that those climate-sensitive regions being avoided. However, to do that, to enable it, we need an information regarding climate-sensitive regions. We need to model it. To this end, several European projects worked on modeling and these algorithmic and these climate-sensitive regions, and the latest one which we participate in it. I'm in flight team 4E. The latest version of ACCFS stands for Algorithmic Climate Change Functions, were developed to model the climate-sensitive regions. There are these ACCFs, algorithmic climate change functions, quantify the climate change per flown kilometer or per emitted mass of species. Here is the dependency of these algorithmic climate change functions on weather data. In fact, we calculate these ACCFs based on standard weather, based on weather variables. For example, as for ozone, we calculated using geopotential and temperature. And here is the unit. So to this end, we develop a library that takes the weather data and calculates the ACCFs, climate-sensitive regions, and these where the reference are provided here. But there is an issue with these climate-sensitive regions. As we know, as I mentioned, these climate-sensitive regions are determined from weather data obtained from a standard weather forecast, which has uncertainty, of course, but the uncertainty are mostly amplified with the calculation of ACCFs. To show that, let's consider these four plots, which are heat map with the ACCFs, I mean the climate-sensitive regions. These are four different forecasts. We can see if one, by looking at the member 3, we can see the green circle, there is no warming potential here. But for the member 1, we have warming potential. So what if one uses the member 4 for determining the trajectory, but the member 1 be the reality? So we will lose much here. So how should we quantify the uncertainty? Ensemble prediction system provides us with n different forecasts, normally 15 to 100. And we can use them to consider the range of uncertainty and use it, employ it in our proposed trajectory planning. Here is the quantification of uncertainty using EPS data. Here is the standard deviation of, sorry, I think the printer is working now. Can you hear me clearly or?
Yes, there is some noise, but it's fine.
Okay, yes, sorry, maybe I can change my location. But here is the standard deviation of weather data, normalized weather data, which shows the uncertainty. The left plot shows the standard deviation of the weather data. We can see that in the relative humidity, there is high uncertainty, it's about 10%. But this is amplified when we use it to calculate algorithmic climate change functions. Here, if we look at the contrast, we can see, and the color bar range for the color bar, we can understand we can have maximally up to 50% deviation around mean values, which is relatively high and can affect the trajectory. So this range for uncertainty has to be considered in the flight planning. To briefly review the literature, I will restrict the attention to the last columns, which is the type of the optimization. In fact, all the previous work on climate optimized trajectory were performed in a deterministic manner based on one forecast. There is a gap in the literature, and as I showed in the previous slides, there may exist an uncertainty, and the uncertainty may be up to 50%. So the determined trajectory based on one forecast may be unreliable or untrusted. However, it's worth mentioning that including all ensemble members, all the forecasts from EPS data, is challenging and of course increases the computational time. So now I want to address our proposed this gap with our proposed robust Ato approach. The robustness that we refer to is in fact means that the computed flight plan will be followed as planned, but the performance in terms of variables such as fuel burn, average time, and climate impact will be impacted by uncertainty. What that means? It means that, for example, we have arrival time. We receive an arrival time with the trajectory optimization, but we can have a range for it. The range means that the worst condition, also we have the worst condition due to the worst meteorological scenario. So we can take into account this information, then decide to fly or not. And this is the structure of our optimization. First, we use EPS data and then use environmental library to model the climate impacts. Then use it to define cost function and feed it to one of these solvers. One of them is heuristic solver, parallel the GPU for the structural space, and the other one is for fuel route space, which uses numerical optimal control based on direct location method. And in the end, by analyzing the result through the Pareto frontier, we can make a decision. So I first start with robust four-dimensional flight planning using heuristic method. This is very fast algorithm thanks to the GPU parallelization. It can provide the results in almost 3 seconds and considers latitude, longitude, altitude, and time for the optimization. Here is an example. I just go to the uncertainties part in which the initial flight plan, initial flight mass are modeled using Gaussian variables, and 50 different ensemble members, 50 different forecasts are considered to represent weather variables. And this is the cost function used in the optimization. Of course, this is the expected value because we have all ensemble members. And this cost function is a trade-off between cost and environmental impact. Here is noted as ATR, stands for average temperature response, which is calculated based on ACCFS. By proper selection of this coefficient CI, CT, CF, we can represent these terms which contains fuel and flight time as a cost in US dollars. And I'm going to consider 2 scenarios, assign 2 different values for EI equals 0 and EI equals 10, which is stands for cost optimal trajectory and climate optimal trajectory. Here's the obtained lateral path. We can see that the climate optimal trajectory chooses different path from cost optimal and shortest path. But to analyze the results in more detail, let's consider this vertical profile, fuel burn, and speeds. We can see that the climate optimal trajectory tends to fly lower altitudes, but as expected, uses more fuel than cost optimal trajectory. But the most important part I want to go through it is the climate impact. We can see that the total non-CO2 effects of ATR within the climate optimal routing is decreased. Not only the mean value, but also the uncertainty, the range. This shaded ranges shows the uncertainty. The uncertainty range is also decreased. If we only consider the mean values, we can conclude that the climate impact is reduced by 62% with an increase of 4.7% in cost. Go through the next approach, robust two-dimensional flight planning. This uses the direct location method. It's the direct approach, and it is for free route aerospace. The cost index considered here is exactly the same as before, but here we have another term called variability in the climate change function. In addition to the expected average temperature response, I'm now including the standard deviation of average temperature response in order to minimize also the uncertainty bound. First of all, I simulate the results for different of environmental index without considering the deviation, I mean the standard deviation. We can see that as we increase the environmental index, the mean obtained mean values of average temperature responses decreases. I picked 3 of them and plot them with the uncertainty. Again, we can contain that, and the method works well. And here is the Pareto frontier. Of course, we will have 3 different trajectories, because now there is, in addition to the mean, we have the max and minimum values, and then we can decide which coefficient is better for flight planning for our purpose. But I want to mention that by increase of EI environmental index, not only the mean values, but we can see the deviation is also decreased from 4.55 to 1.87. In the final case, I'm adding the minimization of the standard deviation of average temperature response. Here, I change it from 0 to 100. We can see that the green one flies higher distances, more distance, but not only minimizes the mean values, the uncertainty is also reduced to a great extent. And if we analyze it through the lateral path, we can see that the green one chooses for both mean values and standard deviation those areas that minimize the mean and also standard deviation. As for the achievements, we have 3 papers in preparation. One of them is almost complete, which is referred to the robust 4-dimensional path planning in the aerospace. The second one, which is 2-dimensional path planning using optimal control, is also the results are ready, and the status is in preparation. We have also working on 4-dimensional path planning using optimal control, but not for the climate impact. Also, the results here is ready. As the future step, we are going to apply this method, the final one, robust 4-dimensional path planning using optimal control to mitigate the climate using for climate optimal trajectory, and I will also work on a survey on climate optimal trajectory plan. This was my presentation. Thank you for listening.